Okay, so well, I will start. So thanks first for inviting me to participate to this session of online lecture within the Acting for Water scheme. Today, I'm going to talk about making use of osmotic energies through the use of forward osmosis. As an emerging process, especially for desalination and water reuse, but that will not be the only topic. I will explain first a few things to give you a broader content. And basically, I will explain a bit what we do here in the research group of Lequia in the University of Girona. Then a brief overview of what is osmotic pressure, also giving you a bit of a history of the development of osmotic pressure processes. And finally, through two projects that we are working on here, using forward osmosis and osmotic pressure, forward factory and concentra, we'll explain a bit what would be the interest of making use of the osmotic gradient. So just to give you an overview, we are in Girona, which is close to Barcelona, so close to France. It's a nice old town, so you're more than welcome to come around. And basically, here we're talking about water scarcity because we have water scarcity issue in Catalonia. If you look at this picture, you could see there is the church in water. And when I arrived here, I thought it was a flood. But in fact, this is a reservoir. So it's an old town that was in the middle of the mountain. And this area has been transformed in one of the reservoirs, one of the big reservoirs of Catalonia, the big dam. And in fact, this is the normal situation when this dam is almost full. So like the last remaining thing you can see out of this old town is the top of the church. So basically, this is how it is in, let's say, normal situation, good situation. And in 2008, that was the situation. So you could see that the full church, and in fact, so it means that there were very little water left in this reservoir. And in 2008, it was a huge drought here in Catalonia. And basically, this is kind of the start of the consciousness of water scarcity here. And this is when they started to push for initiative for water reuse and desalination. So since then, we have desalination plants here around. We also, I think, one of the leading area regarding water reuse in Europe, especially. And in general, Spain is the leading country for water recycling and desalination in Europe. And especially with the needs, apart from the population, but also for tourism and agriculture. So that was the situation in 2008, let's say. So now they build up some desalination plant and so on. And but this was the situation last year in June, so really 1 year ago. And this was even worse. So we had only 2 months of reserve of water. And then it got even worse during the winter, since we still didn't have any rain. So it's the drought emergency started to take some severe measure here at the beginning of 2024. So even with desalination and water reuse facilities, there is still some severe issue with water. Basically, just like personal picture, but just to give you the situation. So basically, during the last months, we had quite some rains, so the reservoir start to fill up again. So it's not so urgent at the moment, and the situation gets better. But still, there is a full consciousness of this water scarcity issue. And probably connected to that, Here in Girona, especially, we have two research laboratories who are focused on water technology. One which is where I work, which is the Laboratory of Chemical and Environmental Engineering of the University of Girona, which is called Lechia. And just next door, there is also the Catalan Institute for Water Research, where they also have a research line dedicated to the technology and evaluation of water technology, basically. So basically, altogether, we have around 70 people, even more, I think, at the moment, dedicated to water technology. And especially here in Lechia, we have more or less 12 people who are working on membrane processes. So the topic we are working on, and I think this is a general topic around membrane processes, is that we are aiming for circularity. And so on one side, it's the circularity of water. So we try to enhance, optimize process for water recovery, but also not only water, but also to try to valorize all the nutrients, pollutants that are present in wastewater, especially, could be urban or industrial wastewater, to make valuable chemicals, to produce fertilizers. So that's one thing, and through the project we are working on, especially now, you will have a bigger overview of it. And we also try to include the membranes itself in the circularity. So we're also working on membrane recycling. So now let's go to osmosis. So basically, what is osmosis? Basically, diffusion of molecules from place of higher concentration to a place to a lower concentration to equilibrate the concentration of these molecules. So if you have a membrane in between two solutions and an extracting solution, you could migrate the water from one side to the other side. And basically, if we look at when we hear about osmosis, normally what we think of is first the reverse osmosis, because this is the process that have been developed. And basically, reverse osmosis, what is it doing is that you have an osmotic pressure, so concentrated solution, which is seawater, in fact, which has a certain osmotic pressure, and you want to remove the salt from this water. So what you do is to put some external pressure, hydraulic pressure, on this concentrated solution, which could be seawater. And then you will produce, you will permeate the water through the membrane, and you will produce fresh water. So this is typically now the state-of-the-art technology for seawater desalination, which is a good step because you can produce a lot of fresh water out of nearly infinite reserve, which is the oceans. But you still need quite some energy through the external pressure to produce this water. And well, this is typically, for example, what we have here in Barcelona. So this is translated in huge desalination plant now. So this is really state-of-the-art technology. There's a lot of those seawater desalination plants around the world. But if we think about it, the question is, if instead of fighting against this osmotic pressure, can we make use of it? So can we make use of this driving force that is the osmotic gradient, osmotic driving force in between two streams? So if we think about it, again, back to this initial picture, you have two solutions, feed solution with the low concentration and a draw solution with the high concentration. If you have semi-permeable membrane in the middle, what you can do, basically you can extract and purify water from the feed solution. So also you have to know that this type of membrane are considered like dense membrane, so high rejection membrane. They are rejecting almost everything except water. So the permeate you will get from this membrane process is of high quality, but you can also concentrate the feed solution. So it could be of use for two types of processes, either to extract water, to concentrate, or even both. And this is occurring with no energy cost because it really relies on the gradient concentration in between the two streams. So when I say no, it's because you still, well, when we talk about industrial scale, you still need to have some pumping, for example, through the modules of membrane modules, but still it really lows. You don't have to add hydraulic pressure. So there are two important characteristics of FO membrane. The first one is that they are dense membranes, like reverse osmosis membrane. So they have high rejection of most contaminants. So the permeate is of very high quality. But the main drawback is that you don't have a pure permeate like you can have in reverse osmosis, ultrafiltration, or other membrane processes. The permeate is diluted with the draw solution. So it's not just pure water, it's water that is permeating through the membrane, which is mixed with the extracting solution. So we have this process, and it's actually, the question is, why isn't it more developed? So the process itself is well known. It's like occurring in many living things, like plants, like the cells of our blood. These are processes which are controlling the transfer of water through our blood cell, for example. So it's nothing new. Also, we have extracting solution. So two of them typically could be saline water. So just thinking of seawater, which is around 35 grams per liter, you have 28 bar of osmotic pressure. So quite high osmotic pressure, quite high driving force. And you can think also of brine water, or even like something like Dead Sea, which is close to the saturation of NaCl, where you can have a very high pressure potential. Also, another draw solution, for example, is sugar. So you have already a lot of just the sugar you have in, for example, in soft drinks. You can already have quite an osmotic pressure, so also driving force. And apart from these, there are many other possibilities. So we have the driving force. We know the process is known. One of the limitations at some point was the membranes. So basically, all the work on membrane and osmotic pressure started in 1959, so quite some years ago. And thanks to the works of Loeb and Sudajan, what they managed is to make some membrane and that make it possible to separate salt from water. And basically, they also thought of making use of the osmotic pressure, but they didn't get good results. But it led to the development of reverse osmosis, which had a huge success nowadays. And but when they try to operate, for example, with more like FO forward osmosis mode, they didn't get flux, and most likely the reason was that the membranes was too thick, and then there were a lot of it was not adapted to the forward osmosis, and there were too much concentration polarization, and as a result, no flux, so it wasn't working. And it's only in the 90s that dedicated forward osmosis membrane has been developed. Initiated by hydration technologies, HTI. If you work on forward osmosis, you probably have seen a lot of publication with HTI CTA membranes. So they developed the first dedicated membrane. That was the start of a new research on that topic, on the evaluation of forward osmosis. And then more recently, other companies developed other type of forward osmosis membrane, more based on simply composites, so like similar to reverse osmosis, with the polyamide separation layer, flat sheet, hollow fiber. But still now, I mean, these membranes allow to have much higher flux, higher separation efficiency than CTA membrane. But still, there is not such a big development of FO now. And nowadays, it's already about 10 years since these membranes have been developed. So why isn't it more developed? Still the question. If you think of when we talk about osmotic pressure, well, you have reverse osmosis, which is about fighting against osmotic pressure. And you also have two processes that can make use of the osmotic gradient, which is forward osmosis and pressure retarded osmosis. Forward osmosis, basically, it's using the osmotic gradient to have the permeation of water from one side to the other side of the membrane. Pressure retarded osmosis is a process that is aimed at producing energy. So basically, you have this natural permeation from a feed solution to a draw solution due to the concentration gradient. And if you apply a slight pressure below the osmotic pressure difference on the draw solution, on the P2 here on this figure, well, you will pressurize your system, and pressurizing the system, you can transform this in energy. So forward osmosis was taught more of water processes to purify or to extract water, while pressure retarded osmosis was expected to be a new type of green energy. So this is what we call like an application of pressure retarded osmosis. So basically, if you think of any river that is reaching the sea, you have on one side a water with low salinity, and on the sea or the ocean, you have high salinity. So you have the two streams, and instead of letting the water flow naturally from the river to the sea, the idea will be to control that with membrane processes and to have the production of electricity thanks to pressure retarded osmosis. Well, you pressurize, you have a turbine, and you can produce electricity. And this process basically has been evaluated even at large pilot scale. I think nowadays maybe 10, 15 years ago. And because of the membrane performances, a lot of pre-treatment that were required at the end, it was difficult really to harvest what was called the blue energy. So this process kind of lost its interest, even though nowadays, for example, there is a startup company in France called Switch, if I'm not mistaken, that is has developed similar but slightly different technology, where they could try to harvest the blue energy. There is also reverse electrodialysis technology that is trying to making use of this energy. So there's still some work ongoing, but pressure retarded osmosis at this stage didn't get much success. And the initial expectation of forward osmosis was also to be an alternative to reverse osmosis for desalination. So at the beginning, people were thinking, okay, now we can make use of the osmotic energy instead of fighting it. But what you do with FO, you basically transfer your dilute. In this case, the idea was to have as a feed solution seawater, and at the draw solution a very high salinity or by high osmotic pressure extracting solution. But this, as I said before, you only transfer the water from the feed to the draw. So then you still need another step if you really want to produce pure water. And so that was called like desalination, seawater desalination closed loop system, which has to be coupled with another process. And at the end, if you play around the energy that you will need for this process, you will always need more energy than what you actually need for simple RO desalination plant. So basically, thinking of seawater desalination like in a closed loop system with a draw circulating in between like recovery and extraction of water from the feed, it could not be really competitive, energetically speaking, with simple reverse osmosis desalination. So And there were also other projects. So like there were especially some fancy NASA projects about urea recovery and water production in the Mission to Mars project. There were also this Omega project where the idea was to cultivate some microalgae into forward osmosis membrane bags. So basically in this concept, you have the sun, you can capture the CO2, you produce biomass, and you have the extraction of the seawater that is purifying, and the wastewater is then transferred to the seawater. So there were this kind of projects, so there were quite a lot of hype around forward osmosis. And basically, if you look at this type of figure that you can see for many business development, new idea development, there are all these phases from the research, innovation, and then finally when it reached the market. And like, I think 10, 15 years ago, this is where forward osmosis was. So there is this peak of inflated expectations, especially because it was expected that you can produce blue energy with PRO and also new desalination technology. So it was like huge potential if this is possible, because when you touch water production and energy production, of course, there is a lot of expectation and a big market potential. Since this PRO and the competitivity of forward osmosis, competition versus reverse osmosis was not so clear, then the expectation went down, and nowadays we are somewhere here. So what's called the Death Valley sometimes, like the process has lost some interest. Even at the research level, people have started to not to get interested in this. But this is where it's also quite interesting, because people are thinking not of this big initial market, but some niche market and some very specific application where it may have some interest. So basically, the initial market or the initial potential of the technology is not what was expected. But nowadays, there starts to have other applications, and there, like the company selling A4 membranes and technology, they start to have to sell some plants. So there is kind of commercial success starting. So what are the current applications and of interest for forward osmosis? I think one of the main interests right now is to use forward osmosis as a concentration process. Basically, forward osmosis, if you enter a diluted stream, you can concentrate this stream, and it could be of interest for wastewater, for brine, for effluents, for liquid food, beverage, proteins. All those applications where not only water recovery is of interest, but also to try to recover your stream, your concentrated stream, which has maybe a higher value, either for nutrients or for food production, for example. So one of the applications is the food concentration, and I think nowadays, like liquid food beverage, for example, I think there are this company in the US, Porifera, started to sell some plants. The interest of the forward osmosis for food concentration is that the only technology that allow to concentrate liquid food without pressure and without temperature. Because normally what they do is that it's evaporation, which can change the taste of the elements, or even high pressure, like reverse osmosis, may affect or change the organoleptic properties of the food. So it's really, in this case, it's not so much about energy aspect or cost, but it allows to preserve the taste of whatever juice you want to produce and to put on the market. Another potential interest is what we call how to treat wastewater streams. So because of high level of pollutants, high salinity, There is the oil and gas water, but also landfill leachate. If you think of the concept of sewer mining, treating manure, brine. So in this case, it could be of double interest to concentrate and to recover resources from this saline brine. And also because these are technology where reverse osmosis can show some limitation because of fouling, scaling, or because of the pressure you have to apply to extract water from those streams. So you can concentrate those streams to very high level thanks to FO, if you manage to have a draw recovery system that allows you to operate your FO unit. Another concept is, for example, fertigation. The interest of that is that in that case, you don't need draw recovery. It means that the diluted draw with the water permeated from your feed could be used directly. So that's the perfect case for forward osmosis, because if you don't need to reconcentrate your draw solution, then you have very low energy requirement for the system. So one of the potential application for that is fertigation. So basically, if you have impaired water source, so wastewater that you cannot use directly to irrigate your culture, what you can do is you extract the water through forward osmosis, and then it gets purified. So what you need as a concentrate is a liquid fertilizer. So you need to put some fertilizer on the plants for them to grow. The fertilizer, they are very concentrated. They have a high osmotic pressure. So in this case, for example, you will use the high osmotic pressure of the fertilizer to attract the water from the wastewater. It will purify the wastewater, and then it will dilute the fertilizer for its application directly on plants. So that's one of the application that is potentially of interest, where you directly make use of the osmotic pressure without the need of draw reconcentration. Then, of course, this process has also some limitation because it's very hard to have a diluted liquid fertilizer, which has the property you will need for the plants. And the last example, which is it's close to the configuration we are working on, it's to combine water reuse and desalination. Basically, nowadays, you have some desalination scheme, you have potentially wastewater nearby, and the idea is that if you have seawater, if you're on a coastal area, for example, where you have desalination plants, well, instead of going through the normal desalination scheme, what you could do is to dilute your seawater with the wastewater, this way through the forward osmosis. So this way you will dilute your seawater, so you will lower down the salinity, and you will lower down the pressure that you will need for the reverse osmosis. And also you have a beneficial reuse of wastewater, so it's like water recycling, and at the top of it you have two dense membrane process on the water recycling lane, because the wastewater, the purified wastewater, will have to go through first the FO and then the RO. So you have high water quality, and you have this multi-barrier protection thanks to these two membranes. Also, because you are protecting, somehow you're diluting your seawater with high purity permeate from the wastewater passed through FO. You will reduce the content of contaminants, and also the membrane fouling on the reverse osmosis side. And basically around this topic, we have two projects ongoing right now here in Girona. One is called Forward Factory, and the other one Concentra. The Forward Factory project is connected to the scheme we just saw before. So it's like to have raw wastewater from one side and seawater from the other side. And within this scheme, we can put 1, 2, or even think of 1 or 2, 3 FO units to extract the water, to have lower pressure operation for reverse osmosis. And at the same time, you concentrate the wastewater. And because you concentrate the wastewater, you can increase the concentration of the contaminants also on the organic matter and maybe ease the recovery or transformation. So we had a few questions when we started this is to say, okay, but how much water, what will be the flux, how much water can we really recover? Depending on what we put as raw solution, what we put as feed solution. And what we saw is that it's not very difficult using seawater as draw solution, wastewater as feed solution, to concentrate up to 10 times your wastewater. And so we did a bit, this was the former slide was more initial calculation, but now we refine all this calculation and we tried with, we did a bit of modeling using different commercial membranes, FO membrane available in the market to try to evaluate where we can do in terms of osmotic pressure, membrane surface area, and especially what is the recovery of wastewater we can expect depending on the membrane especially. What we saw is that with wastewater as feed, seawater as draw, we can easily, it's possible to reach 90% recovery. So 90% recovery for wastewater, it's quite important. Like the actual water reuse plant, they normally operate around more 80, 90% maximum. But thanks to the osmotic pressure of the seawater, we can really extract quite a big amount of the water from the wastewater. So 90% recovery is possible. And then, well, yeah, you can reach the osmotic equilibrium. This is the maximum, it means it's the maximum you can extract. And of course, we will always more or less reach the same level of osmotic equilibrium. But the only difference, depending on the membranes, is the time and therefore the flux and the membrane surface area you will need to reach that. And then after doing this test on how much energy, how much wastewater dilution we can get from the wastewater concentration in seawater dilution, we did some study on the reverse osmosis side to try to evaluate, now that we diluted our seawater, what is the pressure we will need in the hour units. So we used the Leva Plus software, design software, for our reverse osmosis plant design. And we check the impact of having a diluted stream on the reverse osmosis part. So what we saw is that basically, if you have the reference, that is a 35 gram per liter reverse osmosis, even with energy recovery device, you will need around, if it's an optimized system, 2.1 kilowatt per cubic meter of energy to produce water from reverse osmosis with the seawater. And if you manage to dilute it, thanks to the forward osmosis, you can reduce a lot the energy that you will need in reverse osmosis. So by more than 2. In the first case on the left, it's if you want to produce the same quantity of water in the same plant. And then we also evaluate, okay, but if we have the same plant, we use less energy, we have less saline water, maybe we can increase the recovery. Maybe we can produce more water from the same plant. And this is what we saw. It's like we could reach, until reaching the design limitation alarms of the system, we could reach nearly 3,400 meter cubic per hour instead of 1,800 if you use seawater. So you can increase also a lot while decreasing the energy, the production of water on the same plant just by diluting thanks to forward osmosis. So now this is just published. So if you want to have a closer look at it, it's online. And now I talked about energy, dilution, and what we can expect, what kind of dilution and energy impact we can expect thanks to the osmotic dilution. But we also evaluate what will be the impact if we try to implement FO process regarding the wastewater line. So what's going to be the impact of implementing FO with regard, for example, to in this case to granular anaerobic digestion. What we saw is that if we put a FO membrane, we can also within integrated into an anaerobic system, we can increase the COD removal, so we can have a better performances in terms of COD removal. What we have seen in some cases is that in this case, we integrated the FO membrane within the reactor, so we have an increase of salinity in the reactor because the membrane was rejecting most of the salt. And then this led to some release of extrapolymeric substance, which led to fouling. So combining FO within anaerobic biological process might be a limitation at some point, but you can also increase the performances of COD removal. We did also more studies regarding microalgae, so good FO concentrate microalgae. What we saw is that the best configuration we found was to use submerged FO. And in that case, we saw that we could concentrate quite well microalgae, like up to 4 times. And if you have air scoring, aeration in the system, you have very limited membrane fouling, so you can really efficiently concentrate your microalgae. What is true as well is that if we compare, in this case, we compared forward osmosis and microfiltration, and we have similar performances. The difference being that with FO, you concentrate the salt also in the feed, the salt coming from the wastewater. So it could be also a limitation. So there are pros and cons in integration for osmosis with the biological process you may use for the wastewater treatment line. And another project that we are working on at the moment is that working with a company called A4W, which is working on the production of bioplastic from liquid organic waste. And the process is to transform the organic matter in volatile fatty acids, and then with these volatile fatty acids, produce bioplastics. The idea of this project is that depending on the type of effluent and the type of organic waste they have, the concentration of volatile fatty acid could be low or down or high. But in case it's low, maybe we have to concentrate these volatile fatty acids before the bioplastic production. So we've been focused on the increase of volatile fatty acid concentration through membrane process. So in this case, we evaluated forward osmosis, reverse osmosis, nanofiltration to see if we could concentrate this volatile fatty acid and up to which level. So I will not present all the results here because we actually have much more results right now. But basically, we compare for osmosis, reverse osmosis, nanofiltration with a small setup and a slightly bigger pilot. And what we saw is that, well, rejection and the efficient concentration of volatile fatty acid is really pH dependent. It depends on the form of the volatile fatty acids. But basically, if you operate at pH above the pKa of these volatile fatty acids, you have size exclusion by membranes and also electrostatic interaction that allows you for 95 or 94% rejection and efficient recovery. So if you look at RO, we reach 26 grams per liter, starting from 3 grams per liter in that case. So we managed to concentrate it 9 times. With FO, we managed to concentrate 20 times. So we reach very high concentration of volatile fatty acids. With RO, we might have reached much higher concentration, but this requires to increase the operating pressure up to 30, 40, 50 bars. So, but in general, this told us that with FO, especially, you can reach very high concentration of volatile fatty acid and then have a better use of them. So now I'm reaching the conclusion, just to not just about our research, but more in general, a potential of forward osmosis. So like many processes and like many research developments at some point, there were an initial hype that led to the boom and investment in research as well, the technology, and which allowed the development of new membranes, new modules, many things, in fact. But the market itself was not the one that was expected. And then, well, there were the need to focus on niche applications, which doesn't mean that the technology is not useless or competitive, but you really have to find the market where it makes sense. And definitely where it goes now is the use of forward osmosis, thanks to be as a potential as a concentration technology or treatment of complex, very saline streams. And just also an overall conclusion of acceptation, interest of the technology, which is lessons learned about of the overall development. So you have to be critical with the scientific background, but also be critical on the technology you're working on. It's not because you're working on the technology that this is the best in the world. So because you have to think of is it really competitive, or is it competitive with other technology? What are the limitations, the interest? And based on that, you can define where really it makes sense. For example, in forward osmosis, this day we have seen that if it makes sense in concentration process, well, we have to also adapt our experiment in the lab to really focus on, can I reach this concentration? Is it really making sense? Not just making a permeability test to see if the membrane is working or not, or if there is fouling or whatever, but really, can I achieve the requirements for this application with the technology I propose, and how to optimize it, and so on. So that was my key messages. Thanks for listening. And well, I guess we have time for questions, if there are any. Thank you.
I have a question. Can I ask?
Yes, sure.
Okay, thanks for the interesting presentation. My name is Uche Obina. I work for Save Leeuwarden, so we'll be happy to welcome you guys soon for the summer camp. I would, my question is about the whole desalination thing. You mentioned brine, of course. So, I mean, what is the situation? Because you talked about reuse of brine. So in large quantities, isn't this going to be a big problem, brine? So that was my question.
For desalination in general, you mean?
Yes.
Well, it is. I think it is already. It is in two contexts. I think brine, like the brine, especially from desalination plant. It's a problem in the areas where you not really for desalination, but when you put reverse osmosis to even for water reuse or for industrial RO applications, where you produce a brine and you're in the middle of in the middle of the land, so you cannot really discharge it and you don't know what to do with it. So that's already a problem in that context. And well, there have been some controversial study also, but brine discharge of seawater desalination and their impact on the environment. Well, it's still an ongoing debate, but as far as I understood, like for example in the Gulf, they have so many desalination plants and part of the water is maybe used to irrigate, and they are rejecting all the brines into the sea. And because it's a closed sea, they start to see maybe some increase of the salinity of the overall environment. So that may become, apart from the potential impact on the local fishes or environments, also more at bigger scale. So brine is definitely an issue, and there are a lot of initiative now to recover whatever from brine. You can recover, so if you use osmotic energy, maybe you can recover energy from brine because of the high salinity, or you can recover critical materials. Also, if you manage to separate them from the sea salt. But I think there will be also the issue because even if we recover critical materials or whatever from brine, we will end up with piling salt everywhere close to the desalination plant. So, well, this is all around in the discussion of what to do with this brine. Do we go for zero liquid discharge to try to minimize them? I think one of the option and what they are pushing for here especially is that try to do as much water reuse as you can rather than desalination plant. But
yeah, that was my next point, because from our center, what we're actually looking at is water reuse. So, I mean, of course, in areas that are close to the sea, then you have access to seawater, but inlands, because we're actually looking at water reuse for green hydrogen production, for instance, and then where instead of trying to combine it with seawater, we look at direct reuse of wastewater, creating a circular system where you don't have any waste products that you have a problem finding where to discharge. So that's...
Yes. I mean, if you also make the analysis of, because we did that, like if we implement A4 to try to combine water reuse and desalination, can you actually outperform desalination or water reuse or both? And the most energetically, what remains the most interesting is to do water reuse because you have less salinity at the end, and this is what is always more interesting in terms of energy, and also you recover your water, of course. But it's not always sufficient. I mean, here, for example, we cannot rely only on water reuse. And also because of legislation or technology or legislation limitation, we cannot, at the moment, do water reuse for potable purposes. So it's all about overall water management, I guess. Yeah.
Okay, thank you.
Thank you. I don't know if there are more questions. Otherwise, you can continue discussion next week. Anyway, I think most of the people that are in the room will be around.
So I don't see any more questions. So it seems your lecture has been very clear and very insightful. So there are no more questions left open at the time being. So thank you very much for the nice lecture.
Thank you for the invitation. And yeah.
Thanks. Bye. See you next week.
See you.
Thank you very much.
Bye-bye.
All right. Thank you all and bye-bye. See you.